The purpose of today's activity is going to be to find the index of refraction of a rectangular glass prism. So, phrased in the form of a question, as we always do, what is the index of refraction of this piece of glass? The materials are going to become obvious to you as we work through the procedure here, as are the variables. The manipulated variable, one of them, right? We always just have one. The one responding variable and our infinite number of control variables. How many control variables do I expect you to mention? Well, the important ones, right? If there's two really important ones, then I expect you to list two. If there's three, then list three. If there's one, then list one. I don't really care about the temperature of the room and the humidity and whatever. I care about the ones that are really going to make a difference, okay? So what is this going to look like exactly? Everybody's going to have a rectangular glass prism sitting on a piece of paper, a white piece of paper. Just a piece of scrap paper or something with something on the back. It doesn't really matter as long as the front side of the paper is blank. Now what you're going to do with this piece of paper and this rectangular glass prism is first of all draw a little line using a straight edge, which happens to be that glass prism right along here. That's going to be the boundary between the air which has an index of refraction of 1.00, and the glass, which has an index of refraction that we're trying to find. Now what else are you going to use? Well, you're going to need to have a protractor because you're going to need to measure angles, and you're going to need a laser. The laser is going to be fixed right about here, although the angle of that laser is going to change. So for the first trial, we'll say, well, put it right here, shine it into this glass prism. You're going to find that when it goes into this glass prism like this, it's going to refract. Is it going to bend toward or away from the normal line? In other words, is the angle going to decrease or is it going to increase? When we go from air to glass, the index of refraction is going to go, sorry? The index of refraction is going to increase, so the angle is going to decrease, right? So we should expect it to see it bend something like this. You're going to have to determine what those rays look like. You're going to have to measure the angle of those rays, and then you're going to have to record them right here. Now, how are we going to do that? The problem is, first of all, it's not going to be green, it's going to be red. Secondly, you're not going to see this laser beam going through the air because it's not reflecting off of anything. But you will see a little dot right here on this piece of glass, the air glass boundary. You're going to see another dot back here. I want you to put a little dot with your pen or your pencil where you see the dot from the reflection of the laser beam on that glass. The third dot that you're going to draw is right here at the very start where the laser beam leaves the laser. Now, do a little kindergarten work here and connect the dots. Take a ruler, connect these two dots, and then draw a normal line, and with a protractor, measure theta 1 and measure theta 2. Does that make sense? If you have trouble using a protractor, and I know it's been a while for some of you that use a protractor, then just let me know and I can try to help you out with that. Measure theta 1, measure theta 2. What are you going to change? What's your next trial going to look like? Yep. Yeah, move the laser slightly, like not like 2 degrees, but not like 40 degrees either. Change it by 5 degrees, 8 degrees, whatever the case may be. You don't have to change it by the same amount every time, right? Your graphs have to have even intervals, but your data doesn't have to be evenly spaced. So make another angle of incidence, and then see how the angle of refraction changes in response to that. Another one, and so on. And as we almost always do, we have 10 trials here, at least 10 trials. What other data are you going to need to record? Well, medium 1 is air. Medium 2 is glass. And the index of refraction, the known index of refraction of medium 1, which is air, is 1.00. So, angle of incidence, angle of refraction, change the angle of incidence, see what the angle of refraction becomes, change the angle of incidence again, see what it becomes again, and so on and so on and so on. What do you think you're going to do with this?
Make a graph.
Well, we are going to make a graph, but not with theta 1 and theta 2. Because if we plotted a graph of theta 1, or theta 2, I should say, versus theta 1, we're going to get kind of an odd shape, a really odd shape, actually. So what you're going to do is first, before you plot a graph, is create a new table. This new table will be sine theta 1 and sine theta 2. So if theta 1 was 30 degrees, then sine theta 1 will be 0.5. Just literally on your calculator or on your spreadsheet, go sine theta 1. If the second angle was 45 degrees, then we would say sine theta 1 would be 0.707. Do that for all 10 angles. If you want to do it in your calculator, make sure your calculator's in degree mode. If you want to do it on Google Sheets, like we sometimes do, then there's a little trick because of the angles and degrees and radians that I'll have to point out to you. I'll do that later on. Now we're going to plot a graph. This graph is going to be, what's going to go on our y-axis? Alex, what's on our y-axis here? Good. Sine theta 2. And sine theta 1 is going to go on our x-axis. This should produce a straight line. And it should be a really nice straight line as well. As long as you've measured your angles correctly, then you should get a really, really nice straight line here. And then we're going to use that straight line to determine what the slope means. And then you're going to use that to determine what the index of refraction of the glass is. Now, I'm not going to go through that process with you today. We went through that last week with your lens lab. We've gone through it with a number of other labs. You're going to do that yourself today. I'll just remind you that it's going to start with an equation from your graph and an equation from your data sheet. And then you're going to cross things off that appear in both. And ultimately, you're going to get the index of refraction of glass, or N2, is equal to something. So you're going to have a value from the graph. You're going to have a significance of the slope, which is going to take you to the meaning, or which is going to take you to how to find the index of refraction. And then you're going to calculate that index of refraction from the significance of the slope and the number of the slope for the slope that you got for your sine theta 2 versus sine theta 1 graph. Make sense? Finally, you're going to have a conclusion which relates to the problem. What is the index of refraction? And then how do you know? So you've gone through this enough times that you know to just write the index of refraction is 1 point. What would you expect it to be, by the way? It's glass. What would you expect it to be? Somewhere in the range of 1.5-ish. Okay. Water, I think, was 1.3. Okay. It should be somewhere around 1.5, and it should work out to be really close to that, actually. So you're going to say n is equal to 1.41, or whatever works it to be. This is known because an analysis of sine theta 2 versus sine theta 1 produced the slope of this. The slope represents this. So therefore, the index of refraction is this. And then, of course, your sources of error. Let's have 2 or 3 really good sources of error, plus your suggestions for improvement. There was a couple groups that identified something in the last class. As they were working, they fixed them and then kept going. Is that a good source of error?
Yes.
Yeah, it is. Sure it is. Sure it is. You don't have to wait till after the fact and say, okay, I'll fix it this way next time. If you can fix it as you're going, so much the better. You don't have to lose your source of error because you fixed something ahead of time. Right? That's better. It's better to fix it now than it is to fix it next time. Make sense? So what do you got to hand in for this? Well, your problem, which I already gave you, your materials, which are pretty straightforward for this, your variables, which hopefully through the procedure became very straightforward, your data, remember your data is theta 1 and theta 2, your analysis is sine theta 1 and sine theta 2, and then of course your graph, your conclusion, and then your sources of error. One little safety note for this, this is not a It's not a huge deal, but I just want to make sure that everything is okay for you here. We're using lasers for this. Now, these are pretty cheap, low-powered lasers. We don't have to worry too much about, blinding us or anything. If you accidentally got this laser shone in your eyes, if it was for a relatively short period of time, you would be fine. But we still want to avoid doing that. So here's what we're going to do. We're going to make sure that the only time the laser is turned on is when it's sitting on your desk and facing horizontal. Not when you're holding it in your hand, just testing it. It's got to be on your desk and it's got to be horizontal. Does that make sense? Secondly, when you're doing this activity and you're measuring angles and you're drawing little dots on your paper beside the glass and so on, make sure that you're not going down like this to do that. Okay, make sure you're above the level of the desk so that your eyes aren't going to be exposed to this laser light. All right? If an accident happens and you happen to get in your eyes, don't panic about it. Okay, you're going to be fine. Most likely, you're going to be fine. If you show up at school tomorrow with a cane, then I'll maybe change this next time and be a little more strict with my safety lesson. But as a matter of good habit, we want to avoid getting laser light in the eyes. The problem with that is, right, if you get light in your eyes like that, it does damage to your eyes potentially does damage to your eyes, and you don't even know what's happening as it's happening, right? So you're not going to feel the damage being done until after the fact.